All right, critical column load is our last topic for the semester. So critical column load takes a column that has a pin-pin connection. And remember, this is a column pinned to the rest of some sort of system, either within a building or within a truss. You know, individual truss members can be considered columns because they are axially loaded. Okay, that's what defines a column. So this is connected to the rest of the universe, and if we axially load this column, P, it is going to deform, meaning its elastic curve. It's going to look like this. All right, now if we take this and do some integrations and get some math taken care of, we will find that our equation for the critical column load P critical is equal to pi squared EI over length squared. Okay, and that's for a pin-pin column like I've got drawn here. And this assumes axially loaded only. So P is acting through the center of the cross section. When it is off center, that is an eccentric load, and there's going to be moment involved, and we're not going to cover that this semester. Just a reminder, pi squared is still pi, E is still the modulus of elasticity. I is still the centroidal moment of inertia. And L is equal to the length between supports. Okay, now this is a pin-pin column, but of course we don't live in a world where only pin-pin columns exist. What if we have a column that is fixed at both ends? Okay, connected to the rest of the system like a cast-in-place concrete column, right? Length. We will remember from boundary conditions with slope and deflection for beam design that fixed ends do not allow rotation, meaning that it's going to come straight out here and then kind of bulge out in the middle for our elastic curve for a fixed column. And I'm not labeling these, but I probably should just in case you can't translate from my drawing. So this is fixed column. Okay, we still have this little curve here like we did with the pin-pin column, but it's much smaller. We are going to call this the effective length, or L subscript E. And in the case of a fixed column, it is half the length for our effective length. What if we have a mashup, and all of these are axially loaded with P here? I'm being lazy and not drawing that. Pin, there we go. This is a pin fixed column, and it is also axially loaded, and it has a total length between supports of L. Okay, well, what's going to happen here? Well, it's pinned, so it's going to rotate out here, but it's fixed, which means it goes straight before it rotates out. So we end up with kind of a mashup curve here. This is what happens when I try to draw nicely. Let's take another shot. There we go. So this is the part of the curve that looks like the elastic curve on the pin-pin column. And this will be the effective length for my pin fixed column. And this effective length is somewhere between pinned and fixed. And according to our 4 engineers, that is 0.7 length for a pin fixed situation. Now my last column option is going to be fixed free. So an upright pendulum, fixed free, from the way I have this drawn. But by the way, in the case of the fixed free and the pin fixed, it doesn't matter which side the pin is on or which side the fixed end's on. Okay, as long as one side is pinned and one side is fixed, the effective length is going to be 0.7 of the full length. Okay, I'm going to axially load this. I'm going to make this a full length of L. Okay, and when this is loaded, it's going to bend like this. And that looks funny. 3, 4, until we expand this out. And now what you see here is one big, huge curve, right? That now looks like the curve for pin. And this effective length is going to be 2 times the length between supports. And I have my finger quotes up there because free obviously isn't a support, but it is a support type, right? So here's all of my columns. So now I have this LE, which is the effective length. LE is equal to the effective length. And we'll also see this written as capital K times L in your book. So that means that capital K for the fixed is 0.5, and K over here for pin fixed is 0.7, and K over here for fixed free is 2, if you want to look at those individually. So that's the effective length. A flagpole here that is fixed free. We're going to put a little student on here that is trying to climb up this flagpole that we're going to say has a total height of 60 feet. And we're going to say that the student weighs 200 pounds. And that the flagpole is made of aluminum, so that gives us a modulus of elasticity of 10,000 KSI. And we're going to have a cross section here. Terribly drawn cross section. That has a diameter of 4 inches and a wall thickness of 1/8 of an inch equals T. All right. Find how high can the student climb? I can't spell high. If we assume their weight acts through the center of the cross section. Okay, so making a little bit of an assumption there so that we can stick with our P critical equation. All right, P critical is equal to pi squared EI over effective length squared. So see, we've changed this now to effective length instead of just length because this is not a pin column. Okay, now there's a couple of different ways that I can do this. I can either put in that 60-foot height and solve for P critical and see if it's greater than or less than the student's weight. What I'm going to do, since the question specifically asks me how high, is calculate the effective length directly. And then set my student's weight as the P critical. So 200 pounds is equal to pi squared times E, 10,000 KSI, times I. Okay, I need the moment of inertia for the centroidal inertia for that circular cross-section, that tubular cross-section. So my I is going to equal pi over 4 times radius outer, 2 inches to the 4th, minus the inner radius, 2 inches minus 1/8 inch to the 4th. And I have an inertia of 2.8591 inches to the 4th. So I'm going to plug that in. 2.8591 inches to the 4th, all over the effective length. So this is a fixed free column, which means my effective length is 2 times the length. So I'm going to put in 2L quantity squared. Okay, because L is my unknown, because I'm trying to see how high the student can go. And when I solve for L, I get 593.9 inches, which is going to equal to 49.5 feet. Now, if you're plugging this into your calculator and you're not getting my answers, okay, this is in kilopounds and this is in pounds. So don't forget to multiply by 1,000 pounds per kilopound. And now all of my numbers are in pounds and inches. And that's where you'll get the 593.9.